order to understand how a magnet affects a computer monitor, we must first understand how the monitor is produced. On the back of the monitor there are tiny spots of 3 different colors of phosphor. They are made up of groups of red, green, and blue. By lighting these up with electrons in different combinations, you can produce all the colors that you see on the monitor. There's an electron gun in the back of the monitor that fires the electrons towards the screen. These can be moved using a magnetic field. The magnetic field lets you aim the electrons at the right spot of phosphor and get the right colors in the right place. However, when you put a magnet near the TV, it can divert the electrons away from the original path they were intended to follow. And so the wrong phosphor ends up on the wrong spot, lighting up the wrong color. And sometimes, if you put a magnet near a TV for too long, it can make bits of the TV magnetic, so it will always distort the colors, and that is how the colors stay there and you get the color spots on your TV. However, some TVs have degaussing coil inside of them. What this does is every time you reset the machine, switch it off, switch it on, it resets the magnetism on the screen, and it causes the colors to go back to the correct orientation. And even the Earth's magnetic field is strong enough to distort the colors. If you turn a TV monitor upside down or a computer monitor upside down, when it's switched on, this could also make the colors go wrong and distort the colors. And this shows us how electrons are able to be affected by a magnet, either attracted or repelled depending on the charge of the magnet. Also shows us how a magnet can magnetize a screen, causing prolonged discoloration on the screen. As you watch Sean spin the bucket of paper, think to yourself, why does the paper stay in the bucket? Is it from centrifugal force? If you guess centrifugal force, you're wrong. Centrifugal force is actually a false force. The force actually holding the paper in the bottom of the bucket would be inertia. The law of inertia states that an object moving tends to follow a straight line unless acted upon by some sideways force. Knowing that information, if we use our imagination and pretend the vectors drawn on this whiteboard are actually the paper inside the bucket, we can see that the paper does have inertia and wants to keep traveling in a straight line, and that inertia is the force keeping it in the bucket throughout the revolution. And this shows us that centrifugal force is actually a false force, and the force that allows us to do that cool little party trick where we spin something around in the air and it doesn't come out of the bucket is actually inertia. We're going to use fire to heat up the air inside this jar. That's going to cause the air to expand. When I put the balloon on, it's going to deprive the fire of oxygen, causing it to go out. When it goes out, the air inside of the jar is going to contract, and that's going to cause the lower pressure system inside of the jar and a higher air pressure system outside. So the higher air pressure is going to try to travel to the lower air pressure, causing the balloon to get pushed into the jar. Once all that's said and done, it's going to allow us to lift the jar using only the balloon. And this shows us that pressure systems travel from higher pressure systems to lower pressure systems, and that in science there is no such thing as suction or sucking, but rather a higher pressure system pushing something into a lower pressure system. We're going to start with the pot of already boiling water. We're going to add these 2 ice cubes. Watch what happens when the ice is added to the pot. It stops boiling. But why? It's because of the second law of thermodynamics. According to this law, the heat coming from the burner will always flow to the coldest object in the pot. So in our case, the ice. The energy that was originally being used to boil the water is now being used to melt the ice. This chart will help us better understand this concept. As we can see, when the ice is changing from a solid to a liquid, it is called latent heat, and during this period of time, the temperature is neither rising nor decreasing. So this is why the water is not boiling. However, once the ice has changed from a liquid to a liquid completely, the temperature can begin to rise again, so the water can begin to boil. Now back to our pot of boiling water, where we can see that the ice is almost completely melted into a liquid. Once the ice is melted into a liquid, we'll see the pot of water start boiling again. And this shows us the second law of thermodynamics in action, where we see that energy travels from areas of high energy to areas of low energy. Noise can be heard through walls easily. This is because sound is a series of vibrations that move the surrounding particles. The sound waves carry noise from the noise source across the room to our ears. By watching this short video of water added to the top of a speaker, we can see how sound produces vibrations that allow it to travel through particles. Now that we know how sound waves travel, we know that in order to dampen them, we need an area with less particles for the vibrations produced by the sound waves to travel through. However, creating a space void of particles is not always practical. Thankfully, there's a dampening installation that helps convert the sound waves that travel through it into heat energy, therefore not allowing the sound to travel. And this shows us how sound waves move, and that in order to dampen them, we need a vacuum with no particles for the waves to vibrate, or to convert the sound waves into another form of energy.